Hello, and welcome back to History of Psychology. We're going to have an exciting lecture today on Penfield and Milner, we talked about the origins of brain science, not the fruit of brain science, but the origins. Okay, so we are going to talk about the next generation of brain scientists, Penfield and Milner. Penfield was originally an American, and he moves to Canada. And Milner is an English person, and she was born in Manchester, England, and she moves to Canada as well. So our story starts in one place and ends in another. All right, I'm going to go ahead and get the slides up, and we'll get started. Okay, well, there we are. All right, let's go with the first slide. So as always, we talk about the scholars, the geography, the lifestyles, discoveries, and the contribution to psychology today. This is Penfield, Wilder Penfield. He was born in 1891. And then we have Brenda Milner, born in 1918. Milner is our first uh, scholar who is alive still. She's 105, but she is alive and thriving in Canada. This is exciting. All right, so a little bit of background information on Milner. In Canada, it's remarkably cold in the winter compared to other areas in the United States. The Canadian government remains closely linked to the UK, as well as is an ally with the United States. Their government is democratic and interacts with the United States. Here on the right is some of Penfield's original equipment that is available to see at the Center for Brain Health at UTD. So this is down towards like Children's Hospital. That's where Brain Health is. It's off of, you can look it up. Okay, so this is his original equipment, an image of it, and right up here is his business card, which is really fun, and he's written some information on it. So these were donations that were made to the Center for Brain Health, which is part of UTD, but it's down in Dallas area. Okay, so let's do a little bit of information about Wilder Penfield. He was born in Hudson, Wisconsin. Both his father and grandfather were physicians, so this really influenced his ideas. So again, the context is really important about how we come up with our ideas and how we move forward into our future life. His mother was a real proponent of his abilities, and she really thought he could win a Rhodes Scholarship. So she really pushed him early on, and she was his champion. She pushed him to be a well-rounded person in sports and academics. You can see him here with the football, and this is when he was at Princeton. He was at Princeton University. He studied medicine, and then he went on to Oxford University, England, with his Rhodes Scholarship that his mother really, really wanted him to have. In 1917, he married his wife Helen, and she's here right here with him. And this is them in doing a Red Cross event in Paris, and they traveled as part of an organization to help and benefit the war during that time period. She passed away 1 year after Penfield. They were married for 59 years, and they were teenage sweethearts. Penfield moved to Quebec, Canada in 1928, eventually creating the Montreal Neurological Institute. During his time when he was in Paris, he was on a warship and traveling across, and there was an event and he was captured. Later on, he was given a large amount of money in response to his time as a captor. And he used all that money with his wife to buy a large piece of land in Canada, and is still the family compound for the Penfield family. Their children have houses built on the land, such as a large piece of land. And this is important because Penfield and his wife would go back and forth between Quebec and where the university was in Montreal, and they had a really lovely lifestyle, and they were very close with their families. Okay, so this is our background information. He is a well-rounded, original American football player that goes on to become a Canadian. He has some many tremendous discoveries, but we have a very exciting opportunity right now. We have a guest lecturer. Um, he is a professor at the Center for Brain Health and the Brain and Behavioral Science Department. And Dr. Krasik is going to be able to give us more in-depth information on the neurological and cognitive factors on Wilder and Penfield, I'm sorry, Penfield and Milner's discovery. So here we go. Yay, Dr. Krasik.
All right, thank you. I am happy to be here and happy to talk about these interesting discoveries by both Wilder Penfield and Brenda Milner, who, of course, knew each other and worked closely during Penfield's lifetime. So, uh, when we talk about Wilder Penfield, the important things to think about with his methods were that he's a neurosurgeon. So at this time, particularly in the 1950s and the 1960s, epilepsy was a major problem, as it is today, and there were not things like um, deep brain stimulators like we would implant nowadays. So, what it resulted in was a lot of neurosurgeons having to essentially, within the theater for surgery, stimulate parts of the brain or damage parts of the brain. These were the tools that they had available to them. So the awareness in the 1950s was that the brain is a large electrical network that was clear to people and that you could stimulate it using um, an electrode. And so that was both the recording of brain data from neurons, but also the actual stimulation of brain areas that would occur. And what's important to remember about neurosurgery is that you don't put the patient under. They're basically awake, which is important because so many things within the brain um, are very tied together. So if you're going to do any sort of surgical procedure, you really want to make sure that you're um, cutting an area that's not going to disrupt language or knock out memory if at all possible. So they would actually talk to the person while they were operating on them, which is kind of an amazing thing to think about. But that was the way things were done, and it's an important part of brain surgery to make sure that you do not further disable the patient through, you know, removing something you shouldn't. And what would be observed is that when he would Penfield stimulating these areas of the brain, and occasionally for certain people, they would have these really vivid recollections, like a memory was unearthed while they were in the surgery theater right there. And all that happened was an artificial bit of electrical stimulation had occurred within the brain. Now, this didn't happen for everybody, but it did happen vividly for some of the patients undergoing surgery. And so that was a thought that perhaps they were actually memories that were, deeply ingrained within the person's life, and that by stimulating the brain in a certain way, you could unearth or awaken a memory that had been long dormant. And so this also resulted in people questioning, maybe we never lose memories and they're all just available only under certain conditions. And that, of course, is still up for debate. How permanent is memory and how much does it change? But Penfield's work did result in a lot of thoughts about that topic. Okay, so another important element that we think about with Wilder Penfield is that he had stimulated the what's known as the motor cortex as well as these primary sensory cortex. And these are located at the middle of the brain, sort of right across the top of your head. It's sometimes known as the motor strip, which is an area of the cortex that is mapped onto body parts. And the neurons in those areas actually project out to the hands and the legs and other parts of the face, the tongue, in order to actually carry out movements. And so when you had someone in the neurosurgery theater, you could stimulate areas of that motor strip and they would actually move their hand or move their fingers. And in doing that, Penfield was actually able to map out what areas of the brain seem to associate with what areas of the body. Likewise, you could stimulate areas um, just behind the motor strip, and that is the primary sensory cortex. So people would report that, oh, someone's touching my arm right now, or someone's touching my leg, but just by stimulating those cells that receive inputs from the limbs and from the body. And so, just through careful stimulation and listening to what patients reported, he was able to map out the geography, basically, of those motor and sensory areas. It's called the homunculus. So this is the map that Penfield was able to produce when he and his colleagues would do these stimulation or recording sessions in the surgical theater. And it's essentially on the left is the um, how the left hemisphere was thought to be organized for the or rather, I guess that's the right hemisphere. Well, no, it'd be the left in this case. The somatosensory is that area that's highlighted in gray right over here. And it is receiving inputs from all these different areas. You can see that we have a lot of sensory input from the face, very much from the mouth and nose and eyes, very large hand representations and finger representations, and then relatively smaller inputs from the arm, the shoulder, and the torso. And then the leg is relatively less represented also. And so it sort of fits a body representation, like the body's just sort of draped over the top of the brain. And this is a cross section showing the cortex. But then oddly, the head is sort of tacked on at the bottom here, and the genitals are also in a strange place, just after the leg ends and the toes end. So it this is what's known as the homunculus, and you can think about this. It makes some sense that our nose and face and upper lips are very sensitive, so they have a really big representation in sensory cells, whereas areas like our forearm or a lot of the trunk or neck are just not as um, sensitive, and so that's represented within this map. Over here on the right, we have the motor cortex map, and that's just forward of the somatosensory map. So you can see it right here in gray. And it looks relatively similar. It's sort of draped in the other direction. And it's similar in that it has very large hand and face regions, and they're sort of arranged in kind of a similar way to what he had seen in the somatosensory. And again, the difference is these are going to be neurons that send signals to these areas to move the hand, move the face, etc. So these are the maps that were produced in the surgical theater by Wilder Penfield. Now, what's interesting about this is you can look at neuroscience textbooks pretty much through last year, 2023, and they were unchanged. They were the Penfield maps. Basically, like almost 100 years worth of neuroscience had not changed those maps. Only very recently in 2023, work by Evan Gordon and colleagues reported in the journal Nature had reported the inter-effector zones along with a modified cortical map of that primary motor cortex. And that's shown here. It's known as the integrate isolate model. And this is listed as 2022, although the actual report had come out in 2023. That's showing Penfield's view of the motor cortex that has the body sort of draped over with the large single hand region moving into the head and face, and then down into the um, regions of the jaw and tongue. It was thought to be this way for decades. And then only recently was it realized that it's actually basically like Penfield had said, but there are some differences. Most notable, there's an action body center right between the end of the legs and the beginning of the arms. There's another one at the shoulder to eyes transition, and then yet another one after the eyes. And the action slash body would be some sort of overall movement. If you think about lifting some um, box off the ground, you're not going to just do that with your hands or arms. You're going to use your whole body and your trunk and your legs all together. Or if you're doing some kind of large movement like squats or deadlifts at a gym, it would make sense that you'd have some sort of overall body movement area. And that is indeed the case. So with functional neuroimaging, within modern studies, and many people contributed to this, they were able to learn that actually there's sort of this symmetrical mirror relationship where the foot area has leg areas mirroring it, as do the hand. You have arm and shoulder representations on both sides. And the face is similar. It's like a mirror image of the face. That's different than what we saw in the original Penfield diagram. And then, of course, those action body representation areas occupy those three different zones. So this is the new model. But notice the importance of what Penfield had done. He actually had it right for much of the way the body is laid out. Now, the reason that Penfield didn't perceive the action slash body areas, the so-called intereffector zones, um, they're missing from his model because when you stimulate the intereffector areas, you just don't see any movement. I mean, you'd imagine that like the whole body would move like a puppet, as in that diagram, but it's not the case. Those are involved in whole body movements, but you can't get a body movement from just stimulating the area as Penfield would have done. So the neurons seem to be silent, and in fact, Penfield had actually reported that half the neurons he stimulated didn't seem to control any one area, and so he was likely stimulating those action body intereffector zones and not really seeing any evidence of movement, and so he didn't include it within the map. He also didn't have the mirroring. For whatever reasons, the original map just had a single hand, when in reality now, from the revised map, we know that the arm continues over here. So just Penfield and his colleagues in the neurosurgical theater 70 years ago were doing these stimulation studies to produce this long-standing map that lasted for decades in neuroscience. And it took about 50 scholars to produce this revised map using functional neuroimaging, as well as studies within monkeys and EEG, lots of modern neuroscience techniques in order to produce this revised map. So really interesting bit of neuroscience history and important psychological history, because this is all about how we move and how we perceive the world. So Penfield is known for those contributions, as well as just being a really prolific mentor of many surgeons and scholars and neuroscientists, as well as a prolific writer. Um, every time you think about brain locations or take a neuroanatomy class, you come across Penfield's work, especially in the motor cortex and the somatosensory cortex. And within memory, he has quite a profile in making people think about the fact that maybe you can actually retrieve a memory from artificial stimulation. That was really new at the time. Okay, so let's shift over to Brenda Milner, who also was doing her work in Canada and still is. Brenda Milner is over 100 years old now, and still up in Montreal. I was told that Brenda Milner actually lives in the same apartment that she's lived in for most of her life. And she's walks to the McGill campus, still is active as a scholar. And so she's really a model of consistency, just talking about decades and decades of somebody having a lot of discipline and basically continuing to do her work, for an unbelievably long time. So she's originally British, went to Cambridge University and got a master's in experimental psychology. And then she moved for her husband's work in the 1940s, did her PhD at McGill University up in Montreal, Canada. And her work was occurring at the same time as Wilder Penfield was active in surgery within McGill. And she did study with him and graduated with her PhD in 1952. And she's really quite an interesting figure and neuroscientist. Here's a quote from her. I'm still nosy, curious. And she is really delightful. There's some nice interviews of her that you can probably find online. She has a lot to say, and she's remarkably active for someone who's as old as she is. Now, let's talk a little bit more about Brenda Milner's work. Whenever we think about Brenda Milner, we're thinking about memory. She's contributed tremendous amounts to understanding of forms of memory and the characteristics of memory. And a lot of her work is associated with a legendary patient, HM, whose name is Henry Gustav Molaison. And Molaison lived from 1926 to 2008. So he had quite a long life. And he was known as HM within the literature. So when Brenda Milner and her colleagues worked with HM, they would publish, and his name wasn't published within scientific journals. It was only after his death that it was revealed his name was Henry Molaison. So we can think of him as Henry or patient HM, as he was known for most of his career as a subject within memory studies. He is certainly the most famous subject probably to ever be in a psychological study, and he was in dozens and dozens of studies over the course of his life. The reason for that was he had this bilateral removal of two-thirds of his hippocampi. The hippocampus is an area of the brain, and we have two of them one on the left, one on the right. Both were largely removed, and that was done in 1953 when he was 27 years old. So you can see that he lived to 2008. So 55 years of being a very disrupted person when it came to memory. And so he is the most famous case study in memory research history. A little bit about the hippocampus. It's depicted here in the light blue. So this is looking into the brain. The temporal lobe is the major area of the brain in red here. And deep, kind of buried within the temporal lobe, would be the amygdala, and that's this dark blue area. Looks sort of like a maybe the size of a jelly bean, and it's a set of cells that are highly active for emotion. Connected to the amygdala is the hippocampus, which has these ridges, and then it has this tail that basically projects up into the midbrain in different areas. And we have them on both sides, as I mentioned. And so the reason it's called the hippocampus, that's Latin for seahorse. And you can see that if you were to dissect the hippocampus and flip it, I guess that would be turning it about 180 degrees. You can see that it does have remarkable similarity to a seahorse. So that's a good way to um, remember that the hippocampus translates to seahorse. And it's just the anatomy kind of looked that way. And so early neuroanatomists called it that. And it wasn't really understood that it has a critical role in memory until HM, and Brenda Milner came along. So this was a patient who was up in Montreal at the Neurological Institute having a surgery that was performed by William Scoville. So Scoville and Milner were the two names associated with this very early report on HM. And what they were trying to do is treat his epilepsy. So epilepsy is a very debilitating condition, results in seizures, and the seizures will tend to begin in the temporal lobes, the medial temporal lobes where the hippocampus is. And the hippocampus is pictured here. And it's a very electrically active area. Our hippocampus is known to be highly active throughout the day, and particularly at night, it seems like it's um, associated perhaps with consolidating memories. And with that high level of electrical activity, it can result in a seizure. It's kind of the origin point for seizures. And neurosurgeons and neuroscientists at the time were aware of the seizures beginning on one side of the medial temporal lobe. And then what it would do is cross over to the other hemisphere. And then you'd have a full body seizure, which is called a grand mal seizure, which is more debilitating and more troublesome than a more limited type of seizure. So, what Scoville was trying to do is remove a lot of the hippocampus, thinking that that would help reduce the epilepsy. And so that's what they did. And you can see these are cross sections, basically coronal slice through the brain, sort of in line with the face. And you can see um, on the right side would be a typical hippocampus and amygdala, and all of the different slices will show some level of hippocampus or hippocampal gyrus, which is what the larger structure is sometimes called. And over on the left is the removed area. So you could see that they've drawn in where the hippocampus was taken out by Scoville. And this was done on both sides for HM. And that was critical because both sides gives you a much, much different memory impairment than if it was only one-sided. And later in his life, when MRI technology came along, they could take actual scans of HM, and within a person who did not have surgery, you can see that the hippocampus is going to show up gray in those coronal slices. These are the coronal slices of HM, and you can see that they took out the vast majority of his hippocampus on both sides. So that actually did benefit him in terms of his lack of epilepsy. This was effective in reducing the epilepsy. The trouble is, it came with a tremendous amnesia that he experienced the rest of his life. So after surgery, he had what's known as anterograde amnesia, which is he was unable to record new memories as his life unfolded, and he was really densely amnestic. He simply could not remember what would happen from day to day and week to week after he had this surgery. Now, his amnesia also did occur in a retrograde fashion as well, meaning he lost memories that he had prior to the surgery. And he was very densely amnestic, meaning he lost what would have happened several weeks prior to the surgery and certainly within the days of the surgery itself. And he did have some loss of older events that were within a couple of years prior to the surgery. But he did have intact childhood memories and remembered his name, remembered his autobiography and things like that up roughly until age 27 when he had this surgery. Also, somewhat notable was that he had intact working memory. So, in other words, if you gave him a string of digits or a set of letters to remember, as long as he rehearsed it, he would be able to do that. So, he did have some forms of memory that were incredibly impaired, while other forms of memory seemed kind of intact. That's important because if you talk to HM, um, when he was alive, he actually would be able to follow a conversation and contribute to it. And he would do that largely with his working memory. And certainly, if you got him telling an old story about his childhood, he would seem relatively unimpaired at that. It's just that once his working memory rehearsal was disrupted, it was like an etch-a-sketch where it erases everything, and it would be like starting fresh with him. So Brenda Milner had done the majority of the work studying HM, and she was able to report that even with thousands of repetitions, HM or Henry was unable to learn new facts. The doctors and Brenda Milner would have to reintroduce themselves each time they met with him. And he was really never sure where he was for very long. And you can imagine how frustrating this must have been. Here's a quote from him. Right now, I'm wondering, have I done or said anything amiss? You see, at this moment, everything looks clear to me, but what happened just before? That's what worries me. It's like waking up from a dream. I just don't remember. And so what he's reflecting here is the fact that his lack of hippocampus function is preventing him from knowing what had happened earlier in the day or even just moments ago. So when he would leave the clinic, he just wouldn't even remember that he'd been there. And he was eventually able to have a feeling of familiarity for some of the people that he worked with, but they would have to reintroduce themselves no matter how many times he had met them before. So, other facts about HM, and this is from a whole variety of studies by Brenda Milner. He believed he was about 30, so he'd be surprised later in his life when he looked in the mirror and he was in his 50s. He relived fresh grief each time he heard of his mother's death. So, even highly emotional things that had happened post surgery, he wouldn't be aware of. He spent a lot of his time just watching TV and sort of doing passive things, and he had a decently pleasant life, but he did say he wasn't truly happy. He could sense there was something missing. It's just that his memory was so profoundly damaged that he really didn't quite know what. So again, Brenda Milner was responsible for most of the studies on HM, and these were really groundbreaking studies. They became very well known within neuroscience and neurosurgery. No one was ever going to do that bilateral hippocampal surgery again. That was for sure. This was a one-off. Nobody knew it was going to cause such a memory deficit for HM. So that was important from a surgery standpoint to realize we won't do that. And also, Milner continued to visit with Henry throughout the rest of his life, and that enabled her to have an enormous impact on memory research because he was so extremely well studied. And there are just many, many really important reports on human memory from Milner and her colleagues that really changed the landscape of how we think about memory. Some of the major lessons that we learn right away from Milner's reports on HM is that, first of all, short-term or working memories are different from long-term memories, and they don't require the hippocampus for formation. So the fact that I can repeat a phone number in my mind doesn't really rely on the hippocampus because HM could do this even post-surgery. Secondly, we learn that long-term memories are stored throughout the brain, but the hippocampus is necessary for the information to reach that long-term storage state. And once a memory is permanently stored, the hippocampus is no longer required. How do we know that? Based on the characteristics reported by Milner on HM. Remember, his childhood memories and memories of his adolescence and early 20s are pretty much intact after the surgery. So he's got no hippocampus functioning or very limited amounts left. The vast majority of it is gone on both sides, yet he's still able to um, recount major events from his life. So the memories are there and they must be stored elsewhere throughout the cortex. And later research would confirm that seems to indeed be the case. And critically, you do need the hippocampus for the transfer of those memories up into very long-term storage. So people talk of the hippocampus now as having a critical but time-limited role in memory. So it's important for formation, but it's not necessarily um, needed for long-term maintenance or even retrieval of the memories. Okay, so other interesting facts came to light over time. So Brenda Milner was working with him and realized after many, many repetitions of certain kinds of skills, he could remember new things. So this was quite revolutionary, and it speaks to the dedication of Milner in her work. If she had just done a few early studies, that would have been remarkable anyway. Would have learned an awful lot from the early data on HM, but the fact that she was so committed to studying him resulted in yet another revolutionary discovery that there's something called procedural memory or implicit memory, and that is intact for HM. So this is a kind of memory that's marked by an inability to describe the memory. So if I ask you to describe, how do you serve a tennis ball? It's extremely hard to say. Well, you throw it up and you kind of move your arm around, but you can't really describe the motor movements. Similarly, if you try to describe riding a bicycle, um, you could sort of say what your limbs do and how you try to balance, but there's no way to really describe the capability of it, and it doesn't go away, right? If we're a good tennis player, golf, good with a golf swing, good with riding a bike, we have those skills for life, and they're really hard to talk about. You just kind of know them when they are used. That's what's known as a procedural memory. It's a memory for a procedure, like swinging the club through and contacting a ball and hitting it onto the fairway, for example. That's something HM was able to do, and he was capable of that, and it suggests something different about that form of memory. Riding a bike is not the same as remembering the the experience of learning to ride a bike. So HM had a problem for what are known as declarative or explicit memories. Anytime there was a new event, he would have problems learning it, but he could do these other kinds of things. So Brenda Milner had a good idea for an experiment. There's this skill called mirror tracing. What she would do is have a little diagram like a star, and HM would have to look in the mirror and trace around the star. This is really difficult for people because it's looking into a mirror image and it's extremely hard. It kind of messes with you. It's not the way you would normally do this. And so people are really klutzy on the mirror tracing. Like anything, though, you can become good at it. If you practice many, many times, you'll get good at mirror tracing, and then you have that as a skill. That's what's known as an implicit memory. You can't really describe how in the world you're able to trace around the star looking only in the mirror. Um, HM was able to learn this. So after many repetitions, he had no idea he'd ever done this before, but he was getting very fluid at the tracing. So he was picking up the new skill, and it was not based on his hippocampus because that was extremely impaired. So he would think that it's just easy. That would be his explanation. He's saying, I've never done this before. It's just pretty easy. And in fact, he would have forgotten the fact that it was really, really bad for him and really clumsy, and he'd done it many times before. So he had no recollection of that, but his hand could make the movements very fluidly. So he was able to acquire these implicit memories. Another example would be looking at a abstract picture like this. It's really hard to tell what that is. But if somebody shows you a outlined version, you realize, oh, that's a cow. And then when you see this later, you right away remember it or see it as a cow. And so he was able to pick up on these kind of perceptual inputs as well. So he actually was able to record those memories. And that led to the important dissociation or distinction between the explicit memory and the implicit memory. And this has been known about and published on for about 30 years, really intensively. And it all started once again with Brenda Milner and her work with HM. The explicit memory involves the hippocampus. implicit memory doesn't need to involve it. So, really importantly, this indicated brain data or neurosurgery data could inform memory categorization, really verifying it through a biological method. Okay, so really critical work. And what this also suggests is that over time, memory should be studied as a set of different capabilities. And indeed, it was in the 1970s, 80s through the present. So explicit memory divides itself into what we think of as autobiographical memory, something like a memory of your birthday from when you were 16, and semantic memory, just the knowledge that most people typically will learn to drive sometime around 16. Semantic memories rely on the hippocampus, as do autobiographical memories. And those are different from implicit memories like a procedural memory, like a tennis serve or a golf swing or riding a bike. And critically, this is very different work for psychology, which had traditionally done a lot of studies with completely healthy individuals. By studying this one case study, Brenda Milner was able to really verify biologically these things are different. And so her work had a tremendous influence throughout neurology, neurosurgery, psychiatry, and psychology. Enormously famous case study and really pioneering work. Making her one of the most important memory researchers that we've ever had in the field. Her work also involved other important brain organization principles, notably evaluating language in the brain. And you would need to do this for neurosurgery. As I mentioned earlier in the lecture, if you're going to do some kind of removal or some sort of surgery on a brain area, you really want to make sure you're not going to damage someone's language centers. And so Milner is also known for the WADA test, which is a way of testing for hemispheric functions. It's also known as the Wada-Milner test. Wada was a Japanese researcher who was also associated with this procedure. And what you would do is actually anesthetize one hemisphere and then see, can the person still speak? And again, the person would have to be awake to do this. And so it's sodium am amibarbital, which is a basically an anesthetic that would be applied to one of the hemispheres through the artery, so it would get taken up into the hemisphere, and it would essentially put one of the hemispheres to sleep, and then you could verify, is this the language hemisphere or not? And this is related to work that you've already covered on Broca and Wernicke, two very early medical doctors who realized there are these language centers. Broca's area tends to be for production of language, the motor processes involved in speaking, and Wernicke's area is more for comprehending language and adding fluency to language. And both of these areas are typically on the left hemisphere for most people. The vast majority of us have left-sided Broca's area and Wernicke's area. And it is related to handedness. So if you're a right-hander, 95% of right-handers have that left-sided language specialization. So it co-occurs with the dominant hand. The left side of the brain is largely responsible for governing the right hand and the right side of the body because the brain, the neuroanatomy is cross-mapped. And so that dominant handedness seems to go along with having a specialization for language on the right side. And left-handed people, it's not mirror reversed where 95% of left-handers are right specialized. It's 50-50. So their handedness seems related, but even half of the left-handed population are also left brain language specialized. So most of the time, people are experiencing language or producing language with the left hemisphere. But if you're going to be in that 5% that are right brain specialized or the 50% of left-handers, you really want to make sure you know which hemisphere is responsible for language before you do neurosurgery. So the WADA test was a way of accomplishing that. And you might wonder what's the other side doing, right? Just as a this isn't really Brenda Milner's work, but just so you know, we do have an analog to Broca's area on the other side, and it tends to be involved in pronunciation or emotional tone for language. So any sort of prosody that occurs seems to be governed by the other side. And we know that from if someone has damage to the non-language specialized hemisphere, so if they're left language specialized, like most of us are, if they had damage to what would look like Broca's area on the right side, they will speak with a very monotone, flat affect. That's what seems to happen. Okay, so just to recap Wilder Penfield's interesting work, very famous neurosurgeon who was involved with all kinds of conditions, but notably improving life for people who had epilepsy. Wilder Penfield is pictured in the suit up here in this image, and here are some of his um, surgical tools and instruments in this picture. And these are actually in Dallas. If you're ever down near Love Field Airport, the Center for Brain Health has a nice display showing some of Wilder Penfield's instruments. He also contributed to our understanding of how the body's organized within the primary motor cortex and the somatosensory cortex, and an enormously prolific scholar and mentor of many individuals who would contribute both in the surgery realm and in neuroscience more broadly. So really the major thing that you always hear about with Penfield is these cortical organization maps, but also the evoking of a memory in a very rich, detailed form from those open head surgery patients that he was working with. Brenda Milner is really legendary within the memory community. Her work with HM paved the way for understanding all these different divisions that psychology has now gotten used to, like implicit memory versus explicit memory, semantic and autobiographical memory being different than working memory. And it was fascinating within one study, within that one individual, and just an enormous amount of basic memory research was accomplished. So you really can't read any sort of papers on memory without some kind of involvement with either citing Brenda Milner's work with HM or doing work that's related to it closely. And with that, we'll sign off. So this was a little bit of a walk down memory lane from an era at the Montreal Neurological Institute in which the great neurosurgeon Wilder Penfield was busy helping people with epilepsy and revealing the organization of motor and sensory cortex. And all the while, with Scoville's surgery on HM and then Brenda Milner's amazing studies of him over decades, we learn all about the organization of human memory. So I hope you've enjoyed this and go out and build some memories.